Hey everybody, let's take some notes on loop the loop. So let's suppose we have a loop the loop that starts with a ramp. So we go from the ramp down through the loop, and we want to successfully do that. But we want to know what is the minimum height that we need to make it through that loop. And we're going to assume that we don't have any friction. So in order to figure out how to do this, we've got to do some physics. So let's start with some free body diagrams. So for our situation here, let's look at a couple of different spots. So the ball's going to come in this way, and let's have the ball be right here at the very bottom of our loop. So at the very bottom of the loop, we are going to have a force of gravity that points down, okay, and we're going to have a normal force that points up. Okay, notice I have my color codes where blue is the normal force and my reddish color is the force of gravity. Okay, so now the ball is going to continue up. Now it's going to be on the side of our loop. Okay, our force of gravity is still down, and it is still the same size, so I'm going to try my best to make it the very same size. But my normal force is not the same. Normal force, remember, is perpendicular to the surface. My surface is on the right side of the ball now, which means my normal force is going to be to the left. Okay. As my ball continues up to the top, my force of gravity, also known as my weight, is still down, still the same size, but my normal force is perpendicular to the surface. It is going to be down, and it might be smaller than it was before. Okay, and then we continue back around over here. Okay, force of gravity is still down, and my normal force should be to the right this time. Okay. So we have these four different situations, and the force of gravity is always pointed down, but the normal force moves around, and it points towards the center of the circle because of this. So the normal force is going to help us help our ball move around that loop. So through most of this loop, it's the normal force that's going to be making that ball change direction. Okay, but we get an interesting situation, and that's apparent weight. So if we were rolling through this loop, we would feel our weight different. Or if we were on a roller coaster, we would feel our weight appear to change. So apparent weight is the weight you feel, and that's going to be based on the normal force. So when we're just sitting around or standing around, our normal force is usually equal to our weight, our force of gravity. So that's our regular feeling. When the normal force is greater than the force of gravity, that tells us that we feel heavy. And when our normal force is less than our weight, we feel light. And if the normal force is so small that it's zero, that's when we would feel weightless. So notice at the top of our loop, that's when our normal force got the smallest. So if that normal force was so small that it was zero, the ball would feel weightless at that point. Okay. So let's talk about what makes things go in circles. So when an object is going in a circle, that is centripetal force. So it's the force that describes the force that causes an object to move in a circle. The centripetal force is always caused by another force. So in our loop example, it would be the normal force and sometimes the gravity that would be causing it to go in a circle. But we would never draw the centripetal force on a force diagram or a free body diagram. Okay, so let's dig into centripetal force. Let's start with an equation. So the centripetal force is equal to mass times the centripetal acceleration. Okay, but we need to know what is the centripetal acceleration. So centripetal acceleration is equal to the velocity squared divided by the radius of the circle that it's going through. So the velocity would be how fast is that ball moving around that circle. So that's sometimes called the tangential velocity. But that's how fast that ball is moving around the circumference of that circle. Okay, so if we have these two equations, then we can combine them together and we can get this final equation down there at the bottom, which is very fun. Okay, so let's get these out of the way and let's get back to our question that we started with. And that is, what is the minimum velocity? So what is the height that we need to get through a circle, a loop? And so we're looking for the minimum velocity when the normal force is equal to 0 at the top of the loop. So when a ball goes through a loop, it can go through that loop at many different velocities. But we can find the minimum velocity required at the top of the loop because that's the most important part to know if we can successfully make it through a loop. That'll happen when the normal force reaches 0. Okay, so let's take a look at that one point. Okay, so let's do our free body diagram. So we have our force of gravity, also known as our weight, pointed down, and that is the only force that is acting on our ball because we said we're going to go so slow that the ball is not going to push it on the ramp at all at the very top of the loop. So that means that only the force of gravity is going to cause our centripetal force in this location. Okay, so we have our free body diagram. So we need to set up a coordinate system. So let's say that down is going to be the positive y direction, and then x we can make whatever direction because we don't have any forces there. So our net force in the x direction is 0. And our net force in the y direction is the force of gravity plus the normal force, and that equals mass times acceleration. But we have no normal force, so that means that part's going to be 0. We know our force of gravity is equal to mass times gravity. So then our equation becomes that. So the force of gravity, mg, is equal to the centripetal force, which is mass times the centripetal acceleration, which is v squared over r. Okay, so we can do a bit of simplification there. Let's bring that over there. So notice that we have an m on both sides. So we can cancel an m, so we get g equals v squared over r. Okay, and we're trying to solve for the velocity. So velocity squared is equal to the gravity times the radius. So taking a square root, we end up with v equals the square root of gr. So from that, we need some numbers to play with. So if the radius of the loop is 15 centimeters, that'd be 0.15 meters, then we can plug that in and we can solve for the minimum velocity required to make it through our loop. So that would be the velocity at the very top of the loop. We just plug it in. So square root of 9.8 times 0.15, and our calculator tells us that is a velocity of 1.21 meters per second. Okay, so that tells us that as we're going through the loop, the velocity at the very top of the loop needs to be 1.21 meters per second. Is that the velocity that the ball needs all the way through? No, because we know the velocity should be changing as it goes through the loop because it's changing its height. And using conservation of energy, we know that as we change our height, our kinetic energy needs to change, which means our velocity is going to change. So the ball will be moving the slowest at the top part of the ramp. Okay, so our question at the very beginning that we were trying to answer is how high on the ramp do we need to what's the minimum height for the ball to make it through the loop? So we found the velocity at the very top. We still need to work our way over to this height. So in order to do that, we need to do some energy stuff. So let's start with the energy of the ball at the top of the loop. So when it's at the top of the loop, we know it's moving because it has a velocity, so that's kinetic energy. And it's up high, it's above the lowest point, so it's going to have gravitational potential energy. So we can pick those equations, and if we know the mass of the ball, which I'll give you right there is 0.075 kilograms, then we can plug in all of our numbers. Okay, but where did this 0.30 come from? I thought our radius was 0.15. Well, remember, radius is 0.15, but the height of the top of the loop would be 2 radiuses high, also known as the diameter. So that's where our change in y, which is our height, should be 0.30. Okay, so doing our math, we add the pieces together, and we should get a total energy of 0.2754 joules. Okay, because of conservation of energy, we know that that number, which should be equal to the energy at any other point on that loop. So energy before equals energy after. So we know that the initial starting point of the ball on the ramp should have this amount of energy, assuming we don't have any friction. So the energy of the ball at the top of the ramp now should be all gravitational potential energy because we're starting with an initial velocity of 0. So that's our gravitational potential energy equation. We rearrange and solve for delta y, which is the height, which is going to be how high the ball starts from. Our gravitational potential energy is going to be the same number that we had before. Okay, this total energy, because energy before equals energy after. And then we plug in our other numbers. So we plug that in. We should get a height of 0.37 meters. Now, does that number make sense? Should it be higher than the highest point in the loop? Yes, because at the highest point of the loop, it needs to have both gravitational potential energy and kinetic energy, so it should be higher than that amount. So this looks like a good number. Okay, so there's a lot of parts here, but to solve it, let's go over it. We need to figure out what velocity was required at the top of the loop. Then we use that to find the total amount of energy at the top of the loop. And then we were able to work backwards and solve for the height of the ball in order to make it through that loop. So if we go anything higher than this on the ramp, the ball will definitely make it through the loop. Okay. Good luck. Remember, you can pause and go back anytime you needed. Watch it as many times, take notes, and work on your practice question.